Swayam Prabha. Digital India. Educated India.
Good afternoon. So, in this lecture, I will be talking about extraction in a single stage. Okay, single equilibrium stage extraction. This perhaps is the most simplest extraction operation. We could represent this stage as a circle here, and a feed F enters here. Feed F with a mole fraction of C in the feed as XF. And then another stream that comes to the stage is the solvent, and we denote this solvent with S1, and the mole fraction of C in the solvent is YS. Now, these two streams are allowed to mix. So, the two streams are mixed intensely in this stage, and then they are allowed to phase separate, and then they are taken out as two streams. So, we get raffinate and extract. And the raffinate we describe as R1 with composition X1, and the extract with letter E1 and Y1. So, this operation, the single stage extraction, can be either a batch wise or it can be continuous. It can be held in both ways, batch operation or continuous operation. For batch operation, the feed F, the solvent S1, the raffinate R1 and the extract E1, these are all given in the units of some mass, some kilogram or some pounds. For continuous operation, these variables are given in terms of mass per unit time, okay, in terms of mass flow rates. Then we say that the stage is equilibrium stage. So, what this means is that the raffinate and extract composition are in equilibrium. Here XF, this is the weight fraction of solute, that is component C in the feed. YS is the weight fraction of C in the solvent. So, if the solvent is pure, YS is 0, or if the solvent is reused from the previous operation, it may contain a little amount of C. Okay. So, YS can be either 0 or non-zero. X1 is the weight fraction of C in the raffinate. And Y1 is the weight fraction of C in the extract. So these are the nomenclatures that we would use in this particular operation. So generally the question that we would like to ask here is, we might ask how much solvent is required to change the composition of the feed from XF to some X1. Okay, let's say you have 10% of the solute in the feed, and let's say you want to decrease this solute concentration to 1%. So you ask how much solvent should be used. Okay, so that's a kind of design question. Other question would be that how much amount of raffinate and how much amount of extract are coming out of this operation. Okay, so these are the kind of questions that we like to ask in these operations. It is also good to represent this process in the triangular phase diagram. So what is shown here is this triangular phase diagram. So these are the apex points representing the pure components A, B, C respectively, and the blue curve here is the binodal curve that demarks the single phase and two phase region. Now as far as this single stage operation is concerned, so we start with the feed. The feed is a mixture of only A and C. The solute C is present along with the solvent A. Okay, so it's basically a binary mixture, and the binary mixture will have to be identified along the AC line. So this is feed, and you can read the composition here as XF. The other stream that is entering the stage is the solvent. If the solvent is a pure component, you can identify the point in the apex, but if it has some finite amount of Ys, you can identify it here. So this corresponding value is Ys. Okay, so we are taking this F at a mole weight fraction of XF and take the solvent at a weight fraction of Ys. We mix these together, and when we mix these two together, often the mixture will lie inside the two phase region. Okay, if you add very little amount of solvent, you might end up somewhere here, which is a single phase region, and this will not lead to any phase separation. Okay, so this is not a viable place. On the other hand, if you have too much of solvent, you probably be somewhere here. Again, you are outside the two phase region. Again, separation will not be possible. So there is a limit of solvent that you can use such that the mixture will be identified within this two phase region, and the mixture will lie along the red line. What is the red line? The red line is the one that connects the feed to the solvent. Once you mix them with certain proportions, you can identify the mixture to be at some point M. But this is an unstable mixture, it will phase separate. Okay, it will phase separate such a way that our extract and raffinate phase will come out. The gray line that is shown here is the tie line or the equilibrium composition line. So E1 kilogram of extract and R1 kilogram of raffinate will phase separate, and you can read the composition of raffinate here as X1 and the extract composition as Y1. What is shown on the right hand side is the same information, but on a rectangular coordinate. So now what we will do is, we will say that if F and S1 along with XF and Ys are known, we would like to find out what is find E1, R1, X1 and Y1. Okay, so this is a design question. From operation point of view, we can specify certain kilogram of feed with some mole fraction XF is mixed with a solvent of S1 kilogram with its composition of Ys, and ask at equilibrium what would be the amount of the extract and raffinate and what would be the relative compositions X1 and Y1. These are the questions that we would like to ask. So the way forward would be, I will first describe how we are going to do it and then I will show the mass balance. The algorithm is the following, that we connect the point F and S along this red line, and then find out the place of M. If I know the amount of F and S and the relative composition, the composition XF and YS, I will be able to find out where this mixture composition is, and then I will have to find a tie line that goes through this point M. Okay, there are infinite number of tie lines in this two-phase region, so I have to find out a tie line that will go through this point M. If I find that tie line and the tie line cutting the B rich phase and A rich phase will tell you what is the compositions, equilibrium compositions X1 and Y1, and then if I know the composition X1, Y1, XF, YS, I can apply mass balance and find out what is E1 and what is R1. Okay. So basically, to answer this question, we are going to do two steps. First step is to find where this mixture point M is. Second is identify a tie line that goes through this point M, and from there you read the X1, Y1 compositions, and then from there you find extract amount E1 and the raffinate amount R1. So to do this, we will resort to mass balance. So the total material balance for the single stage is the following. Total material balance is that F plus S1 is equal to M1. I am using the suffix 1 because this is a single stage. Later on I may want to do multiple stage, I may want to say S2, S3, M2, M3 and so on. So here it is a single stage, so I say S1 and M1 here, and this must be equal to E1 plus R1. Okay, so this mass balance has to be satisfied. Second is we can write the component C balance. The mass of C present in the feed is F times XF. The amount of C present in the solvent is S1 times YS, and that must be equal to the total mixture mass M1 times the composition at the mixture, which is XM1. Now what I can do is I can eliminate M1 from this mass balance. So I keep the left hand side as it is, and then write for M1 as simply F plus S1. So all the quantities on the right hand sides are known. The feed is known, its composition is known, the solvent rate is known, and its composition is also known. So from here we can find what is the composition of the mixture. Okay, so we go back to this diagram here and then read the value of XM1 somewhere here, and then identify a point where it cuts the red line. Okay, so we solve for the mixture composition XM1, and from there we draw a line, we basically find a point M that lies on the red line at XM1. Okay, so that is straightforward. We can also rewrite this equation a little differently. For example, let us see, I write F times XF minus XM1 is equal to S1 times X1 minus YS. So this is basically another way of writing the same equation, and this equation can be useful. Suppose if XM1 is given to you, the mixture composition is given to you, and if you want to find what is the amount of solvent required, S1 is required, you can use this equation. Okay, So basically only one is unknown here. Either S1 is given and you are asked to find XM1, or XM1 is given and you are asked to find solvent, either way. Okay. So now graphically we can find the place of E1 and R1, by which we can find X1 and Y1. Okay, these are all known to us now. Now we need to find what about the mass of extract and raffinate. For this we are going to use the mass balance again, and writing a component balance here, E1 times Y1 plus R1 times X1 should be equal to M1 XM1. So here we can replace M1 as E1 plus R1, and then write E1 is equal to M1 times XM1 minus X1 by Y1 minus X1. So we know all the quantities on the right hand side. From here I can find what is the amount of the extract. Once I know E1, I can find R1 from M1 minus E1. So this is the amount of the raffinate, and this is the amount of the, when I say amount I am talking about mass. Which one? This one? Okay, so what I am saying is, using the mass balance for the line, red line F and S, I identified the location of M. Now this total mass also is basically distributed among R1 and E1, right? So that is what this mass balance means here. M1 is also equal to E1 plus R1, but we want to know what is the value of E1 and R1, which is the amount of extract and raffinate. This diagram will only tell you the composition, not the amount. Okay, so we have to find the actual mass of raffinate and extract. In order to do that, I apply again one more time the mass balance of the other side, which is E1 plus R1 equal to M1. Okay, and then I do a mass balance on component C. So the amount of C present in the extract is E1 Y1, E1 kilogram and Y1 is the weight fraction, right? And then this is the amount of C present in the raffinate, that must be equal to the mixture. Okay, total amount of mixture times its composition. So from here I eliminate M1 by this equation. Okay, so therefore I am able to find the mass of the extract from the knowledge of how much is the mixture. Sorry, M1 is F plus S, right? F plus S1. This is a known quantity, E1 by R1. So you are right. So what I have done here is, okay, I have actually eliminated R1, not M1. Okay, so this must be, let me go back here. You can do this also, I mean you can also do this way, but what we will do is, we will write E1 Y1 plus M1 minus E1 times X1. Okay, and if you do this, then you can basically write this in this form. Yeah, thanks for pointing that out. This should be fine now. Yeah. So okay, let me also repeat this again. So so graphically we can find E1 R1 and X1 Y1. Sorry, graphically we can find X1 and Y1, but to find the amount of the extract and raffinate, we apply the mass balance. So mass balance is E1 plus R1 equal to M1, and then this is the total mass balance, and here we write the component C balance. So here there are two unknowns, E1 and R1. So we replace one of the unknown, let's say we replace R1 through the first equation. So R1 can be written as M1 minus E1, and then we can rearrange this equation and then we get this, which is the amount of extract. And then once we know E1, we can solve for R1 through the total material balance. So that kind of completes the the question that we posed, that given the feed composition, solvent and its composition, what would be the amount of the extract and raffinate and the respective composition. So that basically solve. Now there's one more point I want to add here that talks about the limits of the solvent we can use. So as I said, that when you mix F and S, the mixture composition can lie anywhere on the red line, but the requirement is that the mixture should be in the two-phase region. So now you can see this point D. D is the limit of minimum solvent that you can add. Okay, you need at least this much amount of solvent. If you add lesser than this, you basically happen to be on the left hand side of the two-phase region. So that means you are in the single phase region, no separation is possible. So the location of the point D, this point D denotes the minimum solvent requirement, minimum solvent for the operation. And if you suppose add minimum amount of solvent, then the mixture will be at point D, and there is a tie line that is going through this point M, and you will get an extract which a composition corresponding to this point G, but the amount of extract is infinitesimal, okay, because that is where the first drop of extract is happening. Okay, so you will have a very little amount of extract corresponding to high composition corresponding to point G, okay, if you use minimum solvent. Okay, you are using minimum solvent, but the amount of extract you are getting is very little, but that will be very rich in component C. And where is the other limit? The other limit is somewhere here. Okay, so let us denote this is point K. If you add lot of solvent, you will move along this line. Okay, so this is a minimum solvent point, and then if you add more solvent, you come here, keep adding more and more solvent, you will actually travel along the red line, and this point would correspond to the maximum amount of solvent you can add. If you add more than this maximum, you basically come somewhere here, which is a single phase region. Okay, so we say this point K is the maximum solvent you can add. So at this point, you have to, so the mixture composition is at that point when you add, and then you can draw a tie line. So I draw a tie line here somewhere. So let us say this is a tie line that goes through this point. Okay, so this one would be the composition of the raffinate. And this would be the composition of the extract. Okay, and if you will see, this amount of raffinate would be infinitesimal, because pretty much everything is extracted out and you have the last drop of raffinate. So the use of solvent basically dictates how much extract and how much raffinate we are able to make. If you operate under minimum solvent, you produce very little amount of extract at the highest composition possible. If you operate under maximum solvent, then you have basically a very little amount of raffinate left behind, everything is taken out as an extract. And you can see the extract composition is now very low, okay, because you are diluted with so much amount of salts, so much amount of solvent. Okay, so ideally when we look at this kind of operation, the solvent has to be chosen somewhere in between. Okay, so the shape of the binodal will dictate what is the minimum and maximum solvent that can be used for the system. If I change the solvent, I change the phase diagram. The minimum maximum quantity also changes. Total mass is very less. You can imagine this is something related to the bubble point and dew point we discussed in distillation, where you take a liquid and then you vaporize, go to a bubble point where the first vapor forms at the highest composition, you continue vaporizing it, and then you go to a dew point where the last droplet is remaining, okay, and the rest is vapor. The same way here, the vapor and liquid compositions are replaced by the extract and raffinate. Okay. So, the amount is infinitesimal, because if you just imagine, suppose if you are here somewhere here at point K, if you add just one extra drop of solvent, you are going to the single phase, everything is now single phase. Just before that you have only a very little amount of sorry, I should say this way. So, here you will have very little amount of raffinate at this composition, and this would be the amount of, so the entire mixture is similar to the mixture itself. Okay. So, and operationally we would like to choose a solvent somewhere in between these two limits. Okay. So, now let us illustrate these ideas with an example, a very simple example that we can quickly do it. So, this is an exercise in Treball's textbook, exercise 10.3. The question goes like this. So, it is decided to reduce pyridine concentration of 2000 kilogram of an aqueous solution from 50% to 2% in a single batch extraction with chlorobenzene. What amount of solvent is required? Solve on triangular coordinates. So, what is given? F is given to be 2000 kilogram. It is a batch operation, that is why it is given in mass units, and XF is 0.5. This is a weight fraction, and we want to reduce to the raffinate concentration of 2%, which is 0.02, and the solvent is chlorobenzene. Nothing is said about its composition, so we will consider this as a pure solvent. So, we will say Ys is 0, and we want to find out what is S1. So, we will use this equation here, which I just now discussed, that the solvent and feed weight ratio will determine this mole fractions. So, here in this equation XF is known, Ys is given, Xm we do not know, S1 also I do not know. Okay. So, but some extra information is given, the equilibrium composition X1 is given. Okay. So, we will basically so what is also given in this problem is this ternary phase diagram. So, this component C here, this is pyridine, and this solvent here is chlorobenzene, and I think it is aqueous solution, right? Yeah. So, this must be water. So, what we know we can point out. So, let me also connect this binodal. So, this is an experimental data that is given already to us. So, let us mark the quantities that we know. So, we know that XF is okay. So, XF is 0.5. So, remember for XF, so for the component C, we will use at the right hand side axis, because that is where it goes from 0 to 100. Okay. In the illustration I have given before, I would have said C is increasing from 0 to 100 on the left hand side, but in this plot the component C goes from 0 to 100 on the right hand side axis. So, we have to read the composition on the right hand side. 0.5 does not matter, it is same way. And what else we know? We want this X1 to be 0.02. So, 0.02 has to be identified somewhere here, okay, somewhere it's close to 0, okay, 0.02, X1 is given. And another thing we know is that the solvent is a pure solvent. So, that is this apex. I am going to draw a line that connects these 2 points, solvent to feed. Okay. The feed is a the solvent is a pure solvent, and the feed is at 50%. So, the mixture will have to lie somewhere in this, but we do not know how much solvent we have added. Okay, we do not know that, but we know that the raffinate composition is 0.02. So I need to draw an equilibrium tie line that connects x1 at 0.02 and y1 somewhere. Okay, so that is a little challenging thing because there are infinite number of tie lines, but I have to find a tie line, and that basically goes through something like, so let me first draw the existing tie lines. So this is one tie line. So these 2 points that the red circles here, this corresponds to one tie line, and this is the other tie line. So these are the tie lines that are obtained experimentally by looking at the equilibrium composition of the two phase separate layer. But what we need is, we need a tie line that will go through x1 of 0.02, okay, and we have to do some sort of interpolation here. Okay, so if I do that, I will use a different color. So I find 0.02 for the pyridine concentration. So this is a tie line that I am extrapolating. Okay, it is not there, it is not given, but I have interpolated. So you see that 2000 kilogram of feed is mixed with some unknown quantity of solvent, such that the raffinate composition is 0.02. Okay, so using this information, I am drawing a tie line that cuts at 0.02 on the raffinate side, extend to the extract side here, and this point is the mixture composition. This is the mixture. So in the previous case, I would have said the other way around. We identify the point M and then we identify the tie line, but the problem is here inverse. One of the equilibrium composition is given, so we basically use that information to draw a tie line through the given raffinate composition, and then that gives us point M. Once the point M is known, then I can read the value of xm from here, and this xm is about 0.066. In my notes, this is how it is. I will upload this figure. You can do this by yourself by doing this extrapolation. So once I get this xm, then this equation directly can be used. Okay, so this mass balance we did before can be used because I know everything here. I know xf, I know xm1, ys is 0, and from here I can solve for s1. So s1 by f is xf minus xm1 over xm1 minus ys. So s1 is 2000 times 0.5 minus 0.066 by 0.066. So that is roughly about 13,152 kg. So let me come back to this problem of finding the tie line. So even though we have got this triangular diagram, using this information we can also plot y versus x. Okay, so this is the 45-degree line. Okay, I can use this to find the 45-degree line. So it will come something like this, right? Now to draw the tie line, all you need is corresponding to x equal to 0.02, you find the corresponding the extract composition y, okay, and this is basically your y1 and this is your x1. So from this equilibrium distribution curve, find the corresponding x1 and y1 and identify those composition on these two branches and connect those two. That's how I drawn this green line here. Okay, to draw the tie line, you need this distribution curve. Okay, if you're lucky, if the tie lines are parallel, you can extrapolate directly without this. If not, you have to go to the distribution curve, find the corresponding equilibrium extract composition y1 and mark y1 on this other branch, x1 on the left hand branch, connect these 2 points and look at where this intersects the operating line, which is this f and s line. Identify the point M. Once you identify the point M, you read the composition for here. Okay, so that is what is 0.066. Once you know that, then it's a straightforward substitution. One more example, very similar to this problem. This is a solved problem in the textbook 10.1. So here it says that 100 kilogram of a solution of acetic acid water containing 30% acid is to be treated with isopropyl ether at 20 degrees Celsius. How much solvent would be required to obtain a raffinate concentration of 20% acid? This problem is exactly same as the previous problem. That is, feed is given, XF is given, X1 is also given, because the raffinate should have a composition of 0.2, and we need to find the solvent. Okay, exactly the same. The only difference you will see here is that for the acetic acid water and isopropyl ether, the equilibrium diagram is different. Okay, so to make this little bit different from the previous problem, what I have done is I have solved this problem in a rectangular coordinate. So you can see this is done in a rectangular coordinate. The previous problem was done in triangular coordinate, and the process is the same, exactly the same. So what we know? We know that F is 100 kilogram, XF is 0.3, X1 is 0.2, and find so Ys is 0, find S1. Yeah, I think this is enough. So this is the x-axis here is the weight fraction of, this is weight fraction of B in the rectangular coordinates. So this contains both x and y. Okay, x is read from the blue curve and y is read from the red curve. So in this case, you can see the tie lines are sloped downwards, which means that the extract compositions are going to be lesser than the raffinate compositions. Okay, again, everything determined by the components and the thermodynamics. So what do we have here? So we have to find XF here, which is 0.3. So this is point F. This is the feed. The solvent is pure, that is in this apex. So we first connect these 2 points. So this is like our operating line. And here x1 is 0.2. Okay, so that is I am going to mark the raffinate composition on here on the left hand side. Remember, here I am using rectangular coordinate, and the composition of C in both raffinate and extract both are read from the left hand side here. Okay, on the blue curve. So this corresponds to 0.2, and now I need to draw a tie line that will go through 0.2. Okay, and then extend this and then find the corresponding y1 and then see where that line cuts the operating line. So like the method I said before, I am going to look at the distribution curve. For x equal to 0.2, I am going to find what is y, and then using that x and y, I am going to mark this line. So this line basically cuts at about somewhere at 0.08. So I'm going to say something like this. Yeah. So this is my tie line. This tie line basically goes from point to cuts the operating line somewhere here. This is my M mixture composition, and this is my Y1. So from here we read the value of M xm is 0.122. Okay, so we read this value here. Okay, so this is something like 0.122, and then from here we find S1 equal to F times XF minus XM1 over XM1 minus YS. So F is 100, XF is 0.3, XMN is 0.122, with this we get S1 as 146 kg. Okay. Is it clear? Any question here? Okay. This one last point I want to highlight here is the construction of the triangular diagram. See, one of the important information that we need for calculating the raffinate compositions and solvent ratio, everything, is the experimental data on the equilibrium curve. Okay, so the equilibrium data is typically given in this form. Okay, so you'll see that there is an information on extract layer and raffinate layer. In both phases, the weight fraction of B, C, A. Okay, so C is the component, B is the solvent, A is the solvent in the feed. Okay, and similarly for the raffinate layer also. So these are the set of composition that is given. So what it means is that this particular extract layer is in equilibrium with this raffinate. Okay, for every composition on the extract layer, there is a corresponding composition on the raffinate layer. These are the points that I was showing, two raffinate and extract points, and I'm connecting through a tie line. So this basically is the information that we need. Now, in the textbook or any question paper, you will see that the information of VLE data, LLE data is given in this form. We need to actually convert this into a triangular graph. We have used only the triangular and rectangular diagram, and we need to use this information and plot it in a triangular diagram. It is not very trivial, so there's some coordinate mapping is required. So what I did is that you can Google and find an Excel sheet that converts this coordinates into a rectangular the composition into a triangular coordinates. So all you need to do is you give in this value of CBA, it will convert into x1 y coordinates, and then you will plot this. Okay, so this operation I did it for myself and I given it to you, but you should be able to use this experimental LLE data and plot it in terms of this triangular. Okay, and this diagram here is the rectangular diagram, which is basically looking at I'll share this Excel sheet for you to experiment with, and you can also plot this distribution curve y versus x. Okay, so all three forms, the distribution curve, the rectangular diagram, and the triangular diagram, all can be prepared. Okay, so the experimental data will be given in this equilibrium data. Okay, it has to be presented in different way. And in the two problem I solved, I directly gave you this plot. Sometimes you may have to generate this plot from the experimental information, right? Have you done something similar in any other course before? Principle of chemical process calculations or thermodynamics? Okay, so if not, I think you should experiment with this a little bit. Okay, so I have given all the, I mean, it's kind of a little bit explanatory that, you know, I've also even calculated selectivity based on this composition. You can see the selectivity changes over compositions. These are the coordinates I am using for the rectangular plots. So this is something you don't need, this is something used for some other problems. So, all right, okay, so that's it for today. And there are two more things I want to talk about. One is this single stage, expanded to multi-stage, and also we do counter current multi-stage also in subsequent classes.